Hello, calculus, and welcome to 5.4. All right, this is curve sketching, and this is what I have been making you do the entire time. So before I always drew those little curves off to the side and said, hey, this here will help you understand. This is where we actually put it all together, and you have to do that now instead of just the small part. So let's get ready. You're going to need graph paper, and for your homework, you will have some on the side here. So we're actually going to sketch the polynomials, and they've got 9 steps. We don't actually do all 9 steps. The first part is we look at the denominator and see it's equal to 0. So we're looking for vertical asymptotes. So where's restricted? We always did a y-intercept next. We look at horizontal, most important if we can. Then we check symmetry, which we've never done because they've never been symmetrical. Now the part we actually do a lot of is the first derivative, which told us the max and the mins. Second derivative was our inflection points. We plot the point and graph our curve. So you have been doing this for the last 3 sections, so this is nothing new. Okay, right here, if you have the first derivative, if it's positive, it's increasing, negative, it's decreasing. So increasing, decreasing. Positive concavity means it's going up, and function is decreasing. This is still positive concavity because it's holding water. Negative concavity means it's going down, and function is increasing, so such as this way, and your other curve goes down. It's just when you're adding them together, which you've already done when you plotted your things. So we're going to show you this and the ones that we really don't pay much attention to. So the first part, we have a 2x cubed. We know it's a positive 2, so it ends positive. So we know our graph is going to look something like so. Domain and range, since it's a cubed graph, we know they're both negative infinity to positive infinity, no restrictions. Our y-intercept was the 1, so I graphed our 1 first. So we went here to 0, 1, and we put our first dot. I know I have to put x's because otherwise it doesn't stay on here. I'm not real sure why. Whoops. Okay, the next part we need to look at is the x-intercepts. If this factored, we would do that. Since it does not, we are not, and we're going to ignore that. Asymptotes, most important over most important. Well, since this is not rational, there are no asymptotes. Symmetry, we've never done, because when you plug in the negative x, this becomes negative, and this here stays negative, so one stayed and one changed. Therefore, it is not symmetrical over the y or the origin. All right, this is the part we paid attention. So we did our first derivative of our thing. So our first derivative, let's see if we can get this all on the screen. So we've got 6x squared minus 6x minus 12. We take our first derivative and we set it equal to 0. Okay, we look here and we can divide everybody by 6 to make my problem smaller. Minus x minus 2. Factors of 2 that give you negative 1 are negative 2 and 1. So f of 2 and f of negative 1 are my max and my min. Okay, when we plug in 2, this is where we went to the original using the table mode on our calculator. So we plug in 2 and we actually get a negative 19. We plug in negative 1 and we get 8. This is where we also drew our graph, negative 1 and 2, and we plugged numbers in to see what was going on to make sure we were doing things right. So we would have plugged in a negative 2, a 0, and a 3. So when you plug in negative 2 here, this is negative and negative. So negative times a negative is a positive. That means this one is going up. And then we would have plugged in 0 here and here. So 0 would have given us a negative and a positive, because then a negative is overall. So this one's going down, which means negative 1 is a max. Then we would have plugged in the 3. So we have a positive and a positive, giving us a positive answer. So he's going up, which means my 2 is a min. Okay, let's graph those 2 points while we're here. 2, negative 19, and negative 1, 8. Let's go back up. So we're going to graph negative 1, 8 is here, a turning point, and 2, negative 19. Oh, way off my graph, unfortunately. Here, we'll just put one down here and label it negative 19. All right, so now we've got my turning points and my y-intercept. Next thing we need are the points of inflection. So to find the points of inflection, we do the double derivative. which is 2x minus 6. We set that equal to 0, and we get 1/2. Again, we plug this into our original in our table mode, and when you plugged in 1/2, you're going to get negative 5.5. Okay, as a check, we plug this onto the number line to see. So let's plug in 0 and 1. So when we plug in 0, this is negative. So this is negative. That means he is concave down. And when we plug in the 1, this is positive. So he is concave up, which matches what we already have. So now let's graph 1/2 negative 5.5. Go back up to your graph on the other page. Sorry about that, it was too long to get on one. So we're going to go to 1/2 negative 5.5. In our up concavity and down and all matches. So we go up, we're going to go down through our y-intercept, through our point of, oh, I missed. Point of concavity, please draw better than me. This is really hard because it is not going through the points the way it should. Let's try it one more time, see if it will. There we go. Here we go, through my point of concavity, so it's going to turn to up and then back up. And that is a very rough sketch of our graph. All right, I hope you did well. That is what we have been doing for the last 3 sections. So you should be okay. All right, let's get down to the next one. I'd like you to try this one by your own. So pause it and give it a shot. First step, negative x cubed. So negative x cubed means it's going to end going negative. So it's going to look like so. Right on my y-intercept is negative 10. So we're negative 10. We're going to put our y-intercept. We have too hard to factor, so we don't care about the x-intercepts. And not irrational, so there's no horizontal. Domain is everybody. Negative infinity to positive infinity. All right, so now let's get this thing done. First thing we need to do is our first derivative to find our min and max. Negative 3x squared plus 6x plus 9. Set that equal to 0. Divide everybody by 3 to reduce this a little bit. 2x plus 3. Keep losing my negative. Here, let's divide by negative 3. That would make that a little bit easier to do here. So that's a positive x squared minus 2x minus 3. That's going to factor into x minus 3, x plus 1. So x equals 3, x equals 1 are my turning points, negative 1. All right, so now we're on our graph. Negative 1 and 3. So let's plug in 0, negative 2, and 4. If we plug in negative 2 up here, this is negative, negative, negative times a negative. It's a positive, so this guy is going up. Let's plug in 0. That'd be a negative and a positive. So this guy is negative. So he's going down. Oh, I forgot my negative 1. That's what I'm doing wrong. I am so sorry, children. I hope you didn't make this mistake. Okay, when I divided by a negative 3, that actually changed my graph, and that's not legal. So if I put a negative 3 in here, this is a negative times a negative times a negative, which is a negative, which means he's going down. This is a negative times a negative times a positive, which is a positive, which means he's going up. So negative 1 is actually a min, which is what it should be. Now we plug in our 4. That's a positive, and a negative. which is a negative, which means he is now going down, which means 3 is my max. Much better. All right, now we got to plug those into our original. So we're going to do f of -1 using your table mode on your calculator, f of 3 using your table mode on your calculator. So f of -1 is -15 equals f of 3. When I plug that in, I got 17. So we're going to go -1, -15. Way down here, we'll just label that -15. We're going to go 3, 17. Again, way off my graph. We're going to get better graphs. Label him at 17. So I got my max. I have my point of my y-intercept and my min. Now let's go down and do our double derivative so we can find our point of inflection. So f double prime of x is going to be equal to -6x plus 6. Set that equal to 0. So x is going to equal to 1. All right, so this is my point of inflection. So again, we're going to check to make sure our concavity is correct. So go 0 and 2. When you plug in 0, you get a positive. So this guy is concave up. When you plug in 2, -12 plus 6 is negative. So we're going to get a concave down, which is exactly what we should have. Now I still got to find f of 1 to figure out what that point is. Again, using your table mode in your calculator, you get 1. So we're going to go to f. We're going to go to 1, 1. That is my point of my inflection point. All right, let's draw this guy in. So now when we look at this, it's going to start here. It's going to go down to my turning point, turn through my y-intercept, go up through my inflection point, turn at 17, and go back down. And my concavity and my up and down all match. Life is good. I hope you did well. Okay, let's try something a little more challenging here. This is a rational graph. So a rational graph is a little bit different because now our domain and range changes. Okay, when we look at this, there is no y-intercept because right here, x cannot equal 0. So since x cannot equal 0, that has to be an asymptote. So our first asymptote we're going to draw on here is at 0. So you can draw in this asymptote, like so. All right, now the next thing we got to look for is a rational or a horizontal. Well, if we divide this guy out and get a common denominator, we get x squared plus 1 over x. Well, when we do our asymptote, that's x squared over x, right? Which equals x. That tells us there is no horizontal, but we have a slant asymptote. I don't know if you remember that. To find the slant, you actually have to do this long division. You just ignore the remainder. So x squared divided by x is x. That gives us x squared. Subtract them, and we're left with 1. Well, x is bigger than 1, technically correct. So this is the remainder, so he does not count. So my equation is what's ever up here, which is y equals x, which means my slant asymptote is the y equal x line. So we're going to draw him in. So this is y equals x. If this was like x plus 2 on the bottom, you could have used synthetic division to do it, but we did not. We were not that lucky, so it had to be long. All right, now we're going to do our first derivative. So when you look at our problem, it was really x minus 1 over x. We're going to rewrite that, x minus x to the negative first. So that's our original. When we do our derivative, derivative x is 1. Derivative of x to the negative 1, well, bring the negative 1 down, making that x, and then we subtract, which is -2. This was a plus to begin with. There we go. So now we got -1 over x squared. That's how we got this derivative. Set it equal to 0. Now you got to be careful here. Okay, so when we set this to 0, I'm going to add the 1 over x squared over. I'm going to get a common denominator, so now 1 equals x squared. Right, then I'm going to square root, which means x can equal 1 or x can equal negative 1. So these are my max and my min points. All right, so on our graph, before we go here, we're going to plug in f of 1 into my original. And when you do that, you get 2. And f of 1, negative 1 into the original, you also get negative 2. All right, so I've got negative 1, negative 2 is a turning point. 1, 2 is a turning point. Now let's double check this on our graph. So we're going to put negative 1. We're going to put 1. We also have to put 0 because it's an asymptote. All right, so we got to check something in each section here. So we've got to check 4 points. So we've got to check negative 2, negative 0.5, positive 0.5, and 2. All right, so now when we plug negative 2 into my original, or up here, so if I plug negative 2 in, that's 1 over 4. So this guy is 3/4. So he's positive. He is going up. All right, plug in a negative 0.5. Well, when you plug in a negative 0.5, you actually get negative 3. So he's negative. He's going down. That means negative 1 is a max. Now let's plug in positive 0.5. When you put in positive 0.5, you get a negative 3. So he's going down. And when you plug in 2, you get positive 3/4. So he's going up. So 1 is a min. So negative 1 is a max, 1 is a min, which kind of looks like what my graph should look like. Because if I was going to sketch this in right now, I would go here, hit him, and turn around. He'd be a max, and this guy would be a min. Right, that's what I'd have so far. But let's check concavity. So now I have to do the derivative of this guy. Well, the derivative of 1 is 0. So we're really taking the derivative of 1 minus x to the negative 2. So this comes down. So this 2x cubed. Well, if you do this, it cannot equal 0 because that would cause you to divide by 0. So that means it does not exist. But I can still check concavity on both sides of 0. So here's 0, and we would check negative 1 and 1. Well, if we plug negative 1 in, we get negative 2. So this guy is concave down. When we plug 1 in here, we get positive 2. So this guy is concave up. Okay, does that match what we have? This section is concave down. The other section is concave up. We've done an excellent job. I hope you have too. Okay, try yours. Be careful. It's really a fun graph, but it's quite weird. All right, here we go. So the first thing you should have checked was the denominator. Well, if you notice, there's no way for that to equal 0 because you can't make a squared negative. So there are no vertical asymptotes. So then we go to the horizontal asymptotes. 3x squared over x squared, and that equals 3. So at 3, we're going to put our horizontal asymptote in. All right, we're going to look for our y-intercept. So when this thing equals 0, so if we let x equal 0, right? So 3 times 0 squared all over 0 squared plus 5 equals 0. This is your y-intercept. So it's 0, 0. So right here is a point. Interesting, huh? Okay, now let's do our first derivative. That's what I hope you did. So remember, this here is finding maxes and min, or maxes and min. So first derivative, you have to use the quotient rule. So the derivative of the numerator, 6x times the denominator, minus the derivative of the denominator, which is 2x, times the numerator, all over denominator squared. All right, so when we do this, let's work this thing out. We've got 6x cubed plus 30x minus 6x cubed all over x squared plus 5 quantity squared. Well, this cancels, and we're left with 30x over x squared plus 5 quantity squared. And I need to know where this thing equals 0. Well, this is going to equal 0 at 0, right? Because we set the numerator equal to 0 because the denominator cannot be. So you're really taking 30x equal to 0 means x equals 0, which is weird. That was my my y-intercept. So let's plug in 0. So let's check -1 and 1. Well, if I take -1 and I plug it into here, we're going to get -30 over a positive number, which is negative. So this guy is going down. So he's going down. When we go here, we plug in a positive one. It's 30 over a positive number. So this guy's positive. So he's going up. So this guy is a min. So I know 0, 0 is a min. Not real helpful though, huh? So let's try the second derivative. See if we can get some more points here. So let's do f double prime of x. So again, we have to do the product rule. So we got to take the derivative of the numerator, which is 30, times the denominator, which is x squared plus 5 quantity squared. All right, minus the derivative of the denominator. Now we got to use the chain rule here in order to get that. So we take the 2 down in front, so that's 2 times the inside, x squared plus 5 to the first power, times the derivative of the inside, which is 2x, right? Times the numerator, which is 30x. Okay? All over denominator squared. So that's x squared plus 5 to the 4th power. All right, let's do some math here. So this is 30 times x squared plus 10x plus 25. Okay, we've got 2, there's 60x squared times -2. So that's a negative 120. Right, and then I got to multiply by that x squared plus 5. Okay, still all over x squared plus 5 to the 4th power. Okay, let's keep going here. So now when I do this, let's distribute this dude out. That is 30x squared plus 300x plus 750 minus 120x to the 4th minus 600x squared. Still all over x squared plus 5 to the 4th. We could have reduced this up here actually. See how they all have an x squared plus 5 in them? We could have taken one out and made our life easier, but I didn't think of that in time, so we're still doing it the long way. Now when we do this, this reduces us down to negative 90x to the 4th minus 300x squared plus 750. Oh, this is x to the 4th, and this is x squared. X to the 4th, x squared. Minus 300x squared plus 750. All over x squared plus 5 to the 4th. Did you see what I did wrong here? When we squared this, this should have been x to the 4th, and this here should have been 5 times x squared, which is 5x squared times 2, which is 10x squared. So I had to change my exponents up here. 4 and 2. And then we combined this 2, and then we combined these 2, and 750 on the end. All right, now that we have our derivative, we have to set that equal to 0. So this is minus 90 x to the 4th minus 300 x squared plus 750 equals 0. Take out a negative 30, giving us 3x to the 4th minus 10x plus 10x squared minus, whoops, did not write well, minus 25. All right, let's see if that thing factors. So this is a negative 75, factors of 75 that give us 10, 3x to the 4th plus 15x minus 5x squared minus 25. Let's group these. Okay, I got to move up here. I'm out of room. So let's factor out a 3x squared, giving us x squared plus 5. Let's factor out a negative 5, x squared plus 5. So we have x squared plus 5 times 3x squared minus 5. All right, this one here becomes imaginary. So he does not count. Let's graph this guy. So x squared equals 5/3. So the square root of 5/3 1.3, I think is what I get, plus or minus. All right, so we got 1.3 is our inflection points. So now we're going to put a negative 1.3, a positive 1.3. 0 is an issue, so we are not going to plug him in. And when we plug those in, our 1.29, I think is what this actually is. We get a plus and a minus. So now when we do this, we go up here and we plug 1.29 into our original function. So let's do that. So when we do that, using your table mode again, you have f of 1.29, and you should have got 0.75 point, and f of negative 1.29, you should have got a negative 0.75. So we are here, and we are here. Inflection point says it goes up and turns, and this guy goes up and turns. Isn't that the coolest graph ever? I hope he had fun doing it. He does take a long. We usually aren't quite that mean. All right, let's continue on. Got to do a couple of logarithms here, and then we're finished. I should have probably broken this one down into 2 also. I'm sorry about that. Okay, first of all, we look here. We know x cannot equal 0, so it's an asymptote at 0 because of the denominator. Y-intercept, when you let x equal 0, you cannot do that. So 0 equals natural log of x. Okay, when we do that part, we get x equals 1. All right, so let's go here. First derivative. Let's see if you remember your derivatives of your natural log. So the derivative of natural log is 1 over x times the denominator minus the natural log over the derivative of the denominator, which is 2x, over denominator squared, which is x to the 4th. All right, so we go through here, we cancel this out. They all have an x in common, so we can reduce those to x cubed. Setting this equal to 0 means we only set the numerator equal to 0. So we're going to add the 1, divide by the 2. To get rid of a natural log, remember take the e of both sides, so this cancels. So it's e to the 1/2 power. Plugging that into your calculator, you get 1.65. Okay, plug that into your original, and when you do that, you should get 0.18. So currently, we have a max or a min at 0.18. So we're going to go 1.65, 0.18. So it is like barely above the x-axis. So now when we do this, here we go, 1.65. Let's check 1 on each side. So I'm going to do 0 and 2. Oh, I can't do 0. It's a natural log. I'm hoping you recognize that that guy is a asymptote. Okay, so let's do 1 and 2. When you plug in 1, you get a positive number. So this guy is increasing. When you plug in 2, you get a negative number. So this guy is decreasing. So at 1.65, we are increasing on this side and decreasing. I grabbed that over too far. Decreasing on the other side. Increasing, decreasing. Okay, now let's do our second derivative. Also, again, quite a lot of fun. So you do the derivative of the first, which is negative 2 over x, because that's your natural log of the numerator, divided or multiplied by the denominator. Derive the denominator times the numerator over denominator squared. Now let's just reduce this guy. So that's negative 2x squared minus 3x squared. So that's a negative 5x squared. Okay, they all have x squareds in common, so we can reduce those. And this is our final second derivative. All right, so at our second derivative, we're going to take them, set the numerator equal to 0, add your 5 divided by 6, take your natural log, and that's 2.3. So at 2.3 is our inflection point. So we're going to put 2.3 here. Okay, we've already checked some of these. So now we're going to check 2 and 3. Okay, when we plug 2 into here, you're going to get a negative number. So this guy is concave down. When you plug 3 in, you get a positive number. So he's concave up. All right, and then when you plug 2.3 into your original, so f of 2.3, we plug that dude in, and the answer is 0.16. Not far off. So 2.3 is right here, 0.16. Now we know we come up, we're going to go through here. He's going to go here, he's going to turn. This is an inflection point from concave up to concave down to concave up. If you keep running this along on your calculator, you'll see that it gets closer and closer to 0, but it never ever hits 0, so there's actually an asymptote there. All right, I hope you did a good job. That was really quite hard. All right, your turn. Let's see how you do. Pause and give it a shot. All right, again, this is a really fun graph. I hope you had fun with it. So the first thing I did is I rewrote this so I could see what this function actually looked like. So when you look here, denominator can equal to 0, so that's not a big deal. So, and I also looked here, when I set the numerator equal to 0, that's y, so you x equals 0, you get y equals 2, that's your y-intercept, which is here. If I set the numerator equal to 0, all right, so that's y equals 0 this time, so I find the x-intercept, x equals negative 2. So I can find an y-intercept and an x-intercept fairly easily this time. That was something new for us. So next we did the first derivative. Now remember, the derivative e of x is itself times the derivative of the function, which is negative 1. So the derivative of x plus 1, which is 1, times the original, or e to the negative x, plus the derivative of e to the negative x, which is here, times x plus 2. They both have e to the negative x in common, so I factored that out. That leaves us a 1 minus x plus 2. Distribute the negative, combine the like terms here, we get negative x minus 1. All right, I need to set this equal to 0. Well, we know that e to the negative x can't equal 0. So x minus x minus 1 has to be set equal to 0, which means x equals negative 1. So when I plug this in to my original, I get negative 1, 2.7. So we go to negative 1, 2.7, and here's my point. Now I need to know if that's a max or a min. So I plugged in -2 and I plugged in 0. Well, when I plugged in -2 here, so we're plugging it in, I got a positive number, so it's increasing here. When I plugged in 0, I got a negative number, so it's decreasing. So -1 is a max. So I know this point is a max so far. So far I could draw like here, through here, max, turn, don't know much else yet. So now let's keep going for our inflection points. So I do my second derivative, and I get e to the x times the -1, because that's its derivative, -x minus 1 times e to the -x. All right, nothing too major. They both have a -1 and an e to the -1 in -x in common. So I factored that out. That left us -x minus 1 plus 1. So this canceled. -1 times -x is x. So this is my second derivative. Set equal to 0, and I get 0. Well, I already know 0 is 2 because that was my y-intercept. So I have that graphed. Now when I plug in my -1 and 1, the first one is concave up, and the second one is concave down. So when I go here, I think I just did that backwards. Let's check. Then this guy goes like so, and he approaches my thing. Let's hit pause for a second. All right, I'm sorry about that. When you plug in a -1, you get a negative number, because when you plug in a -1 up here, it's e to the first times a -1, so that's 2.7 times -1, which is negative. This guy is concave down. And when you plug in the positive, this guy is now positive, making him concave up. So that exactly backwards, and I'm sorry. So now when you look at your graph, this guy is concave down, switches to concave up, and he keeps going along this line. If you plugged in your table and you just hit that asks question, you would see it would approach 0 but not touch. Because technically, this here is an asymptote. Very cool. Fun graphs. I hope you're enjoying them. All right, good luck on your homework. Sorry for the long video, and make sure you post questions if you have any.